It is my pleasure to welcome Radek Cichy as today's speaker at MOCO. He has a background in cognitive science, philosophy, and neuroscience, and did his PhD at the Bernstein Center for Computational Neuroscience under John Dillon Haynes. Also, he did a postdoc with Aude Oliver at MIT, and is currently a professor for neurocognitive and experimental psychology at the Freie University in Berlin, where he also directs the Center for Cognitive Neuroscience. He is known for combining various neuroscientific methods for data analysis, multivariate pattern analysis with machine learning models, especially deep neural networks, to get a better understanding of higher visual processes. Radek, the stage is yours.
Great, Alex. Can everyone see and hear me well? Does it work? And I hope you can also see the mouse pointer on the screen. Good. Okay, everyone. Thanks so much, Alex, for inviting me and giving me the opportunity to present you some of the work I've done in the last years, and also some of the things that we're doing right now. The talk is about 45 or 60 minutes. As already you might have heard when I talked to Alex, please interrupt me at any moment you wish, just shout in. So whenever a thought comes to your mind, you think, oh, I didn't get that, or how can that be? No, that doesn't make any sense, or would that also work? Just give me a shout. So, as Alex introduced me, I'm a cognitive neuroscientist working at the systems level in humans, mostly with methods from psychology, neuroscience, and computer science. My research focus is visual perception, and in particular object recognition. That is, I want to know how your brain translates the constant flow of photons hitting your retina into a meaningful perception of the world consisting of entities that are enclosed like objects. For this, I take an approach which I might very pragmatically call better theory through better methods. I want to, if I have a question, make progress by developing or tinkering around with things so that I get a new view or a new access point to empirical data that I can then use to make a better method, which might, or to make a better theory of vision. Now, even if you don't care about vision at all, there might be something in this talk for you, because all of the methods that I will be talking about, I would claim are equally applicable to any other cognitive function that humans engage in. And actually, a lot of people have used many of those techniques already in domains far away from expertise, to which I will sometimes hint. So, from this perspective, from this interdisciplinary perspective, to understand what it means to see object, for me, it means answering three questions. What is happening where and when in the brain when we see? So in other words, what I want is the title of this talk, a spatio-temporally resolved and algorithmically explicit account of visual cognition. And this is something I've been after for the last 10 years, and I presume I will be after in the next 10 years. So how do we go about this? One way to do this would be to measure the brain, and while we see and establish statistical dependencies between visual conditions and what happens in the brain. So because I care about objects, what I would do is I would take a brain, I would show different images to the brain, images of objects because I care about objects, and then I would like to establish statistical dependencies between brain activity and those object images. Now, unfortunately, we do not have direct access to the brain, as you know. Our brain activity is always, or our access to brain activity is always mediated by a particular measurement method. So, for example, if you want to know where something is happening, you would use a technique which has high spatial resolution like fMRI. So let's assume you're seeing this bus here, and we're going to look what is happening in your brain. You might have a particular activation pattern in this part of cortex that looks like this: little activation blue, a lot of activation red. Now, if you, however, wanted to know when something is happening in the brain, you would turn to a technique which has high temporal resolution. Now, fMRI is great in space, but it's not so great in time. But we have techniques which are great in time, like MEG or EEG. So, for example, we could say at a particular time point after an image was shown, again, let's say this bus, we would have a particular activation sensor pattern in your MEG helmet or in your EEG sensors. Now, let's say, okay, we figured now out where things are happening and when things are happening. This by itself, however, does not tell us what is happening there. We don't know the algorithms. And one way to go about this and to cash out this question would be to say, okay, if we had a model and this model had eyes and we showed it the same images that we showed to the human brain, it should in some way activate or work in the same way that the human brain does. Now, it is now the case that we do not have a single technique that answers all of these questions, the where, the when, and the what at the same time. So it is a main current challenge in cognitive neuroscience of how to combine those approaches in a quantitative common framework so that we have an integrated spatio-temporal and algorithmically resolved view. So we basically want to know for any region at any time point, what is this thing doing? Now, this challenge is difficult because there is no simple or direct mapping possible between those measurement spaces. So for example, if you look at this particular fMRI voxel here, there is no way to say that the activity in this particular voxel is directly related to some activity in some sensor of the MEG at a particular time point. Or if you have some model, and I don't care what it is, we're going to talk about deep network models, also because we're in Tübingen and that's probably the epicenter of it now in Germany, or any other model, there's no way to believe that you can directly map one onto the other. So these measurement spaces are incommensurable. So you need some trick to combine information across those spaces if you want this integrated view. Now, which brings me to the content of this talk. First, I will introduce a method, one of two that I will talk about today, which is representational similarity analysis. You had a talk by Nico Kriegeskorte very recently. He might have also mentioned this. This is a method from mathematical psychology, which was then revived by Nico Kriegeskorte in the early 2000s and is now very widely used. And I will use it here towards two aims. First, resolve visual information flow in space and in time. And then in the second, go to explain visual representations in vivo by comparing them to a particular type of method, which is deep neural networks. Okay, good. Then let's start with the first. So what's the trick? What are we going to use to combine these signal spaces to integrate them together? The general idea behind RSA is to transform incommensurable signals from their signal space into a common similarity space. So how does that work? Usually in RSA, you start out with a medium to large-ish number of conditions, large maybe with relation to standard experimental designs in psychology, not large with respect to today's large-scale data analysis efforts, and we will get to that. But let's say something that goes beyond classical psychology, something between 10 and 200. So let's say, again, I care about objects, so I take 100 different objects or so. Then I resolve the brain responses in the signal spaces that give me spatial resolution like fMRI, temporal resolution like MEG, or that tell me something about the algorithm that are going on there. My mouse is dying. Like a deep neural network, like here. So as said, these three spaces cannot be directly related. They are nonlinear related. It's very difficult. So what we do is we abstract from the signal space to a similarity space by calculating the pairwise similarities between condition-wise patterns. So for example, we take this fMRI pattern for a bus and this fMRI pattern for an orange, and we ask, how similar are those? And we can use whatever, in a way, theory or you or an algorithm wishes to be the similarity. So one possibility would be to look at Spearman's correlation. Another would be, for example, to look at classification accuracy. So usually we don't do this in terms of similarity, but dissimilarity, just the reverse. So 1 minus Spearman correlation. And maybe in decoding accuracy, in terms, if you were to use a classifier, you would ask, how well can you distinguish between conditions based on brain patterns? And the idea would be, the better you can do so. So the higher the decoding accuracy, the further away these patterns are in the signal space, the more different they are. So in this way, you can also interact RSA with machine learning techniques. Now, for each pairwise comparison, you would enter the result in a matrix, indexing rows and columns by the conditions compared, for example, bus and orange, and just put the dissimilarity there. And you do this separately for each signal space, for your fMRI, for your model, for your MEG. And now you can think on, okay, maybe I can do this for my ECOG, for my behavior, or whatever else. Now, if you do this for all pairwise comparisons of conditions, you're going to end up with one full matrix telling you where this signal space or which conditions this signal space treats as similar or dissimilar. And therefore, these matrices are called representational dissimilarity matrices. They are symmetric across the diagonal, and diagonal is undefined because the similarity between a bus and a bus is always full. So now these things, luckily, are very comparable, different to the signal space. They have the same dimensions, they live in the same mathematical space, so you can now directly compare those in turn for similarity. And in this way, you can then compare or combine their respective advantages. So you can, for example, build one of these RDMs for any part of the brain that you care about. That can be the whole brain, that can be a single voxel, that can be particular regions that you care about, at whatever spatial resolution you wish. You can do this for model parts, which will give you algorithmic explicitness at the level at which you dissect your model. Or you can do this in MEG for different time points so that you harvest the temporal resolution here. And then you can just compare those RDMs. For example, if you compare then fMRI with MEG, it will give you spatio-temporal maps, where and when fMRI and MEG signals are similar. If you compare fMRI with models, it's going to give you model maps. Where does the model predict activity? Or if you compare the model RDMs with the time point RDMs from MEG, you will get time courses when a model predicts brain activity. Is that general idea clear so far? Do you have any questions, comments on this? Maybe give me a thumbs up if you think that this is reasonable, or okay, sure, it makes sense to you, Alex. What about the others? All good? Okay, I see some nodding heads. Great.
I have a detailed question. So the fMRI and the MEG have to be also somehow matched in time, right? You would probably have different designs because yeah, fMRI is so much slower in time. Mm-hmm. But they yeah, so basically I think my question is how many volumes would you match with one time point in
yes.
this region?
I think that's a very interesting experimental and theoretical question. So the idea is because fMRI and MEG are here recorded separately. If we had EEG and fMRI, we could maybe do it at the same time, but because we do it separately, we can also use different designs. So for example, EEG, we can simulate and record much faster, whereas the bold response is sluggish. So therefore, we might only show an image every couple of seconds, not every second. So the designs are different. And the question is, how can you really compare this? And this is a question of how much you believe that the task context influences your processing in the brain. So for me, and in the data I will show you, we passively look at images, I would say the effect is minimal. In both cases, the participants do an orthogonal task. And sometimes they do it every 3 seconds, sometimes they do it every 1 second. We leave usually the image presentation the same, but even that would not necessarily have to be the case. Now, if you go into higher domains, let's say you go into some decision making, where people are going to more faster or slower integrate towards a bound, that might very much influence the strategies and the brain mechanisms involved. And there it might be much more important to match those things. So it's a question. You can always say, however, and that in a way works in your favor. If you have radically different designs and you do still find commonalities, that speaks towards this being a rather generalizable automatic processing that's going on. Otherwise, it wouldn't fly. So that's maybe, if you want, an advantage that gives you additional confidence in the data, because you're combining data from different potential participants, different days, different modalities. If there is something they have in common, this thing must rather be a strong signal and something that is independent of all the things that changed. But yes, you might miss the thing that you changed if that changes how the brain works. So it's actually not a method. It is not a detailed question. It's actually a core question, depending on the cognitive function you study. Okay. So let's go to our first aim: how to resolve information flow in space and in time at the same time separately, at the same time simultaneously. and applied to the visual domain. So what did we do there? We did the following experiment. We chose a data set of 92 objects that had been used previously by Nico Krieger's cohort, who inherited it from Uzbekiani, who had done this stuff in Monkey, which had a hierarchical structure. There were animate and inanimate objects, which were either human or non-human in bodies and faces. And then we recorded in separate session MEG responses and fMRI responses to those. We resolved those things with RSA in the time resolved way of MEG, in a space resolved way in fMRI, and combined them. So in the first step, I would like to show you how it looks like if we do this for MEG. Let me just start the movie. What you see here is actually the real MEG RDM for every millisecond, and the objects here are ordered on the X and Y axis in different categories, so you can start seeing some structure. This is 92 objects, so a high dimensional space. You cannot think in a high dimensional space or see anything, so we project this high dimensional space onto a two-dimensional space using a technique called multidimensional scaling, so that the distances between objects that are in this high dimensional space are as much preserved as we can in a two-dimensional space, because in two-dimensional space we can look at things. And in this space, we now color the objects with respect to the category they belong to. For example, faces are red, bodies are yellow, and inanimate objects are blue. And now we can look at this RDM for every millisecond with respect to when an image was shown on the screen. And what you see after 6, 7, 9, or 10 milliseconds is basically there is noise. There's a salt and pepper structure in the RDM, and there's absolutely no structure here. Now, after something like 55 milliseconds or so, I see, oh, this thing starts to stabilize, meaning that there is something going on, which is a real process, but you don't yet see a real distinction between red, blue, and yellow. But that suddenly starts emerging at, I don't know, 120 milliseconds, so where all these red dots move out, showing you that the brain treats all of these things differently from the rest of the brain. And later on, as it continues, you find that all hot colors are on one side, and the cold colors, the blue is on the other side, meaning that at this point, the brain starts to care about a high-level distinction, which is animacy. So just with your naked eye, you can see that with a rather large number of conditions, and it was, let's say, a novelty that you can record so many reliable responses in MEG, you can resolve what the brain treats as different or dissimilar across time. You can see it with your naked eye, and based on this, of course, you can do many quantitative tests to then find out, okay, when is it that the brain kicks in at distinguishing between bodies or faces, or between animate or inanimate objects, or transport to other things? Where does the brain start caring about active or passive voices in the sentence, or about different sounds, or whatever it is that you are investigating? Now that we have this view into what is happening in the brain in time, we now want to match it somehow to what is happening in the brain in space. And for this, we do the following. Here, I will present you a searchlight-based analysis for a spatially unbiased perspective. You also had a talk, I think, by, sorry, I have a cold a bit, by John Haynes, I think 1 or 2 weeks ago, who together with Nico invented this searchlight analysis, which we now apply here in a particular way. So to remind you, for the MEG or EEG data, we will have one RDM for every millisecond with respect to when an image was shown. For the human fMRI, we are going to calculate an RDM for every single voxel in the brain. For this, we extract information around this voxel and its vicinity. We build an RDM from this. Now, the two RDMs live in the same space, so we can trivially compare them using, for example, correlation, and then we can assign the similarity between those two to the voxel in the brain, which is the central voxel for this searchlight. Now, if we then shine the searchlight through the whole brain here, redoing this for this MEG RDM, we will know where in the brain patterns are similar to MEG patterns at a particular time point. And if we then do this for all time points, looping across, let's say, time from -100 to +1000 milliseconds with respect to image onset, we will get a movie of how information propagates in the brain. And this is what I would like to show you next. So what you see here is the brain from the top, from the side, from the front. And we would like to see how information flows in there. As you see in the very beginning, there's nothing in the brain as you would expect. because it takes about 50 to 60 milliseconds for the information to reach visual cortex. And it should show up in the back of the brain, as it does, and start spreading more forward. And what we, for example, see here is something like a first wave that goes anterior from the back regions to the motor forefrontal regions. This activity becomes much more widespread anteriorly. Then suddenly you start seeing that the information in the back seems to vanish before it then later on starts coming back. So in this way, for this particular example, we have shown that you can map human brain activity in both millimeters and milliseconds at the same time, using this particular trick of RSA to bind particular data at a particular time point in MEG to data at a particular space in fMRI. Now, this was years ago, so the question is, what's the potential of all of this? And I think Oliver and me have written a perspective piece where we summarize this, and I think there is three ways in which, or three general ways in which this can be used in cognitive neuroscience, and how it could potentially, if you care about it, enrich research. So one of them is, you just take this technique as it is out of the box. It's basically very simple, right? Correlations of correlations, and you apply it in different fields. So we, for example, mostly care about visual object recognition. So we care about eyes and visual stuff. But you can also apply it in different domains. So for example, with Oliver and Santani Teng, they beautifully use it to resolve visual information flow during auditory perception. Santani Teng, with Oliver and me separately and together have also, for example, looked at the blind population and looked at sensory processing. We're just in the process of doing this. This is a long-term project. So we want to know how information flows in the tactile domain. If you, for example, have a medical background and you have people with brain damage, you know that you have a rerouting of information in the brain. You have plasticity. But how is this exactly happening? Now you have an additional tool to look at this. The third way is that you can start looking at lifespan development. So most of our subjects where we establish things are college students. So they are this little thingy in the middle. They're 18 to 25 years old, white Caucasian students of psychology. Now you might want to know, okay, but object recognition as other cognitive functions, they don't fall from heaven, they develop. So why can't we do these things in infants, for example, and see how it then from infancy develops over childhood into adulthood? Now, of course, this is crazily difficult if you ever tried to do fMRI in an infant. But at least, we started with looking at EEG response in infants using multivariate techniques and RSA in the way that we've shown. This is work by seeing here, which we put on archives, and it actually works. And now it just takes some more effort to put the fMRI on top. We're also doing some work together with the MPI for development, looking at the elderly. We know that the elderly have changes in their processing of visual objects, both in the healthy and in the diseased brain, for example, in terms of Alzheimer's, and we'd like to know how exactly that works. Of course, you can apply this, once you go away from this more basic sensory stuff to higher cognitive functions. So for example, people in Finland have used it to map different types of attention. Also, if you get a bit more creative, you can say, we always start now out to look at brain activity with respect to an external stimulus. But what if you wanted to do this towards a behavior? So if you, for example, had a motor response in a visual decision task or after some motor preparation, you could just say, I'm going to look at the EEG, not starting from the external stimulus, but from the response, and then go backwards. What activity is leading towards a particular outcome? And then maybe if you have, in the context of a visual decision task, a visual stimulus coming up, you map the activity starting from the stimulus towards the behavior. You go back from the behavior and start mapping it backwards towards the stimulus, so to get you a full picture of actually from stimulus to behavior. A second way how this can be useful is in combination with other techniques. So for example, you can look at brain stimulation. We're starting to do this where we say, if you believe that a particular region is responsible for a particular function in the human brain, information should be routed through there at a particular time point. If we now knock it out, what happens? Or with other techniques such as eye tracking. The third way how you could do this is you could try to push the boundaries of this. And the simplest way of pushing the boundaries would be to say, I'm going to improve on my resolution in fMRI or an MEG or EEG and try to get at a finer scale. So for example, one way to do this would be to combine layer-specific fMRI with frequency resolved EEG. Now, why would you do this? The idea is the following. We know that there is two cardinal information flows in the human brain, at least in the visual brain, or at least we think that there are, and we conceptualize it this way. One is feed forward from the external stimulus inward, and then something from inward going backwards, something like expectations or your previous experiences. And we know that this feed forward and feedback sweep is very hard to distinguish in the normal brain because it strongly overlaps in space and in time. However, we also know from canonical microcircuits that they are more or less bound to different types of layers. So for example, we know that feedback information in V1 comes into middle layers, whereas feedback information targets more the outer and the inner cortical layers. So if you actually were able to resolve fMRI at the level of layers, you should be able to resolve information at the level of feed forward and feedback. Also, a lot of research in humans and non-human primates has shown that feed forward and feedback information is more or less associated with particular frequencies. So high frequencies like gamma are more related to feed forward activity and alpha beta maybe more to feedback. So now if you put these two things together, so resolve EEG, MEG in different frequencies, fMRI in different layers, you might be able to actually, in the best of all possible worlds, to see something like information flow through this MEG fMRI fusion to the technique I've shown you coming into a middle layer. You would see it then spreading to another layer where it's processed and then spreading backward to yet another layer in the original area. And this is something that is driving us, and this is something like a 5 to 10 year plan for the lab to accomplish. Do you have questions, comments, anything I could help you with?
Hi, could I ask a quick question?
Go ahead.
How is it possible that you could transfer some of this, like let's say models on people who aren't being tested? Like, for example, if I'm not a person who sits and goes through this, the EEG cap, or not going into the fMRI and so forth, is it possible to like transfer that information to someone who has perhaps like, how would you describe similarity between people who are being tested versus who are not?
I think that's a complex question. I can see what I can say about this. So one is, you could cash this out in a very mechanistic way and ask, okay, does this work only in the same people? So do you have to get EEG and fMRI in the same people, or could it be other people, that you get some people for the EEG and some for the fMRI, and then you compare between those two? And the response is, of course, again, it depends on how the brain works. If you believe that what you're tapping into are highly individualized brain circuits that differ from person to person, it shouldn't work. If you take something like the assumptions of classical German experimental psychology, Allgemeinpsychologie, that there is universal human functions like object recognition, which are common to all human beings and are likely solved in a common computational way, then comparing across subjects might be completely unproblematic. You will lose what is specific to a human being, but you will keep what all human beings have in common. Sometimes you just have to also do this. So for example, imagine you want to know something about the letter representations in the blind population, and they get this letter representation from Braille reading or from the auditory sense, and the sighted subjects, which get them from auditory information or visual sense. Then there is no way you're going to present visual information to the blind. But you can take different subjects. One is blind, the other one is sighted, or one is deaf, the other one is hearing. You can present different modalities and you can ask whether they still have similar representations. So in this case, the representations can actually be radically different. And whether this works or not is, of course, a question of how sensitive your technique is and how the brain works. Most often, until now, we do not find big idiosyncratic differences in any of the functions that we study. And it's hard to say what it means. It either means, all people are boring and the same. It might be that the function at the level at which we study them, because everyone is a kind of similar visual world, that they are similar, and they might become very dissimilar once we were, for example, to study personal memories or not take any objects, but objects of personal significance. There's research by Jan Schares pointing towards this. Or maybe we have to improve on the SNR or maybe the task context in which we are doing this. So this would be my answer. I hope that helps a bit.
Yep.
Cool. Okay. So let's go to the second part. So let's say you've done your MEG and you've done your fMRI experiments, part one of your PhD, and okay, for your part for your question of the cognitive function that you care about, these particular components of the brain are involved at particular time points. Then you still don't know exactly what those are doing. If you want to explain what is happening there and what these visual representations represent, one way to do this is to compare them to deep neural networks, because deep neural networks do, or any type of other computation model, embody particular principles that you can then test whether they are predictive of that activity or not. Now, for this to work, you need a model that works well. And you have been likely living with it then, and I don't think you are, because everyone knows that since 2013 or 2014, deep neural networks have taken over, at least as models of cortical visual perception. They are the models which predict brain activity better than any other model out there. So just because it's also, I think, for a general audience, the general idea here is we do take so-called artificial neural networks, which are engineering artifacts created by the inspiration of the brain, but with engineering purposes in mind. For example, what they want to do is you give them an image of an orange and they just tell you, this is an orange. So they have an output of a categorization. They have different stages and they implement often mechanisms that you also find in the human brain, like convolution, max pooling, and normalization. So these things do solve, for example, visual object recognition particularly well. By now, they also solve many other tasks well. So a lot of people started asking, okay, if these models do tasks that we care about so well, do they solve these similarly or differently as the human brain, and in which way? So how would you find this out? Well, in the first step, and that's really only just the first step, but the approach is pretty simple. What you do is you take a set of images, for example, these 118 images here, you record brain activity and you resolve it in space and in time, for example, using fMRI and MEG. You then show the same images to a particular model that you believe or want to test whether it's a good model of the human brain, and you just compare how similar they are. If they are very similar, great, you have a model of human information flow. If not, not. Okay, so how did we do this? We started doing this around 2014, 2015, and I would like to show you maybe two classical results, which then reproduce results of others and have been reproduced by others a million times just to create a common basis. So for example, here we used RSA to relate such deep neural networks to brain activity in millisecond resolution. So again, in the MEG, we will have one RDM and 118 by 118 for the image set that we used. And then for the deep neural network, we looked at the RDM for every layer, because every layer is a particular stage, and we wanted to know how these stages map onto processing in time. And you see the results on the right. So x-axis is time, y-axis is similarity, and the different colors are the different layers. And what you see is that the representations of these deep networks and cortex correlate. So these artificial, very abstracted thingies built for recognizing images are treating the same images as similar or dissimilar as the human brain. Now, you know that these networks have a hierarchical structure. So layer 1 is closer to the pixels, layer 8 is closer to the output. If the brain is doing these computations in time, then the similarity between brains and deep networks should show up with the hierarchical structure. So layer 1 should correlate earlier than layer 8. And this is what we find. So if you plot the DNN layer versus the peak latency, you find a slight positive component, showing you that the order of emerging representations for these networks and cortex is similar. Now, if this works in time, it should also work in space. So what we did is, again, just a search-out approach, asking where is a particular layer of a network similar to brain activities in the brain. So sorry, to activity in the brain. And what you see here is two hemispheres. Red colors indicate high similarity between the network and the human brain, and blue colors low similarity. And what is shown here is actually statistically significant. So this movie just loops through the different layers. And what you can see is that, again, all 8 layers predict brain activity in the human brain. And as you would expect, early layers of the network, layer 1 and 2, predict brain activity in the back of the brain, early processing stages. And the higher you go in the hierarchy of the network, the higher they predict in the human brain as well, which leads us to conclude that the processing hierarchy of these deep networks corresponds to that of the human brain. Now, work such as this and a lot of others has inspired many people to follow in this regard and to just look, okay, what is it about deep networks that is similar to the human brain? How can we use this? And it has, and this let's say, this research has evoked 2 types of reactions. One was very strong excitement on the one side, where people said, okay, great, we now have finally models which predict brain activity better than anything else we ever had. Let's use that stuff. What a unique opportunity. Whereas others said, oh, this is completely useless. You have a model, and there's 10 reasons why they thought it's useless. It has nothing to do with the standard computational modeling we do. Usually we make a particular hypothesis, we test this hypothesis in a model, and then we test it against brain data. We don't take a model with millions of parameters that was made for a completely different purpose and then compare it to the brain and find that it's similar. What do we learn from this? I think you can learn a lot from this. I will not go into this. As Alex introduced me, I have a background in philosophy, and you can get the boy off the streets, but not the street off the boy. So at some point I thought, okay, let's go back to something like philosophical, or maybe at least structured thinking about what models actually do in neuroscience. Read up on what people suggest and read up on what different roles models have in science. And I don't want to go into detail. You might, if you want to read the opinion article in TICS, but I would like to highlight 3 points. I think these types of models have use in neuroscience in terms of both prediction, explanation, and also exploration. And I would like to focus on 3 points here. One is, just by knowing that models predict the brain very well, we gain something, because we can use prediction power as a stepping stone to explanation. For example, if you have 10 different models, and with deep nets you can have many models, some of these will predict better and some of them will predict worse. And then you can say, okay, now that I have a benchmark, which one is doing better, which one is doing worse? I can look at the ones which are doing best and ask post hoc, what about them could it be that makes them best? What are the differences to the other networks that don't make them so good? And form hypotheses that you couldn't have otherwise gotten. An alternative way to thinking about this is actually these models do provide an explanation. They do not provide an explanation in the sense that classical computational neuroscience does, but in a different way. DNNs are defined by very few and highly interpretable parameters, but these parameters are just very different from what you thought previous models are. The parameters are things like the architecture or the training material or how exactly they are trained. They are not the particular weights in a particular neuron. And the third way that such deep nets and the comparison to the brain can be very useful is for a function which is often highly under-evaluated in science, which is explanation. And the idea is, if you have a fully fledged theory, people have been thinking about the stuff you're doing for thousands of years. And there's a well-developed theory. Then from this theory, you can derive hypotheses, you can test it, and everything goes nice and smooth. But if you deal with a field like human cognition, which has been around a few dozens to hundreds years, where the concepts are unclear, what is vision? Where does it start? Where does it stop? How is it different from memory? You know, when does vision stop and auditory stuff start? What is object recognition exactly? So how do you define this? All of these things are, in particular experiments, clear, but overall very vague, and it's unclear how these concepts map onto the world. Then actually, in such a vague situation, there's a lot of space for exploration, for trying out new things, trying out new concepts. And these deep networks can be a great starting point for new theories, because in some aspects, they are the same as the brain. For example, they consist of little entities like neurons. That's uninteresting. In other ways, they are completely different like the brain. They don't have biological realism. They don't have an intricate axonal structure. So in this way, a comparison is also uninteresting. But there are some ways in which we haven't tested how they are similar. These are the so-called neutral analogies. And by fleshing this out, we can learn, for example, a lot about both the brain and neural networks. And I would like to highlight you 2 or 3 different ways of how we go about this, doing this. And the first one will focus on saying we can use this for exploration and explanation. So here I would like to highlight, for example, particular work done by Cichy. Usually the tasks or the networks compared to the brain are trained on one particular task, like categorization. And then you see how similar or dissimilar they are. Now you can ask, what would the different tasks that such a network can be trained on, for example, like in taxonomy, change the relationship to the brain? You can, for example, start ordering them. Say, okay, there's some tasks, there's many tasks in computer vision you can define, which are more about 2D information, like autoencoding, denoising, or finding 2D edges. Some are more about 3D information, like finding the depth, reshading, finding the surface normals, and so on. Some you could call semantic. They care about the object class, so actually categorization, what we started with, or a scene class, and so forth. And then you can ask, okay, if these things actually are different tasks, how do those different tasks map onto the brain? And then Cichy did that and found, and you can see the results here in different colors, the different types of tasks explain different parts of the brain differentially well, which then shows you that the DNN training task, it's one very interpretable parameter, determines where in the brain the DNN explains this representation, and therefore this indicates representational differences and guides confirmatory future research. So for example, you can say, I didn't know what this particular region did here. You could line it out and say, my analysis of these networks showed it's more related to 3D tasks, in particular, maybe 3D key points and 2.5D segmentation. Now I'm going to take this insight and I'm going to refine this hypothesis and target this in future experiments. So one step is just you find out what's happening there, you explain it in this way, and you use it as a stepping stone. Now, you can do something like this on your own, or you can say, I want to do it with others. And we thought, well, if we really want to epitomize on the prediction power that deep networks have, we should not be doing this on our own. We should be doing this with many others together. So therefore, in 2019, we founded, we as Oliver, Gemaroj, and me, the so-called Algonauts project. You can look up the website if you wish. So the idea is that we provide you with all the mechanism that you need, plus we provide you the brain data and the stimulus material so that you can test your particular model, which you believe is a good model of what's happening in the brain, submit the output of that model to our website, and then take part in an open competition and see how well your model is actually doing. Open competitions of this kind are a very common instrument of science and robotics, for example, computer science. In neuroscience, not so. And we believe that introducing such things into neuroscience has large benefit. Also, because it has all the ideas that, for example, are behind open science directly built into it. You don't have to put it on top. It's just already in there. If you start an open challenge, everyone is on par, people submit their stuff, and the best one wins. How much more open could it be? So to give you an idea of how this works, in 2021, we did a challenge. We called it How the Human Brain Makes Sense of a World in Motion. So what did we do? We recorded fMRI in 10 human beings, and we wanted to go beyond still images. So we now went into 3-second clips of human events. Things like a baby crying, soldiers marching, or a panda bear eating something. And then we recorded brain activity in every voxel of the cortex while human beings were watching those videos. And we provided all of this information, we call this the training data, to our participants and said, do whatever you wish with the data. You can take your model and start fitting it to the brain or build a model from this of the brain yourself. And then we're going to evaluate for you how well you actually did. So what we also did, we recorded for 102 different videos. They're called test data, brain imagery, data, which we, however, withheld. So we asked people to then submit the predictions of their models and tested them against our hidden test data to see how well they did. Now you could ask, okay, did we do this with RSA? Yes, we could have done it with RSA. There is no reason not to do it. In 2019, we had done so. However, in 2021, we used a so-called encoding models approach, which I will just shortly introduce it as a second way of how you can relate, let's say, different signal spaces to each other. Whether encoding models or RSA is better or worse, I think is often a rather fruitless debate. I think they have their own particular usage spaces. And for me, there are different tools with different properties, which allow at least me to think different things easier or more difficult. You know, if you take an analogy, you can take a knife to cut a cake, and you can take a chainsaw to cut a tree. And nothing can stop you to say, but you know, you could also take the chainsaw and cut the cake with it, and you could take the knife to cut the tree with it. Of course you can. I mean, you can also build chainsaws, which are like a knife, or you can, you know, actually show that actually in an extreme case, a chainsaw is a knife, and this is all correct. But in some ways, just as they come, at first glance, they allow you to do particular things easier or more difficult, as all tools are, or as all tools do. So in this case, in this particular case, we used encoding models. So to just give you a short idea what we do. As said, we have something like 1,002 videos. We then say, okay, please put those 1,002 videos through your model that you believe is a good model of the brain. Don't care what it is. Can be a deep network, can be not a deep network if you don't like deep networks. And we just look at, and you look at the activations that those videos give you in your particular model space. And then we say, okay, we know these activities, but again, those activities in this model space, these features don't directly map very well. So you can't say, you know, this model feature directly relates to that voxel and this model feature to that voxel. So therefore, we ask you to estimate a feature to voxel mapping phi. So you just ask, okay, I need to take 3 of this, 2 of that, 0.5 of this. And if I add this all together, then I'm going to get activity in this brain region. And you can do this, for example, using just a simple regression model, which the result of it is a mapping that takes you from your model space to the voxel space. Once you have this mapping, you can then apply it to the test set videos. We send you the videos, you look at those, you again put them into your model, you apply your learned phi, which is the mapping from the model space to the brain space, which will give you predicted brain data. And we can just take this predicted brain data and see, okay, how well is it doing actually in predicting the brain? Is your model really as good as you say? And it seems in this way you can actually make some progress. So for example, as the baseline in this competition, we provided AlexNet. Why not? It's an 8-layer network, which is very, very often still used in neuroscience research. And this is the brain regions in the brain. You know, red colors means high correlation between the model and brain activity, where this model predicts activity. And now when we go into this challenge, so people do submit their models, we evaluate them, and then we get a winner. For example, it was Team Huse here, and you can see the difference that there's, you know, up to something like 2 times as much variance explained by this model, also in new brain areas. So therefore, we believe that open challenges do accelerate the progress in biological and artificial intelligence research, because they allow you to do things that you would usually go do a publication at a time in a context where, you know, you can do this just much faster. Okay. So how to make further progress? If you ask people, we need 2 things. One is better models. And for this, we did this Algonauts project. We just ask everyone, please participate if you feel like it. There is going to be another Algonauts competition 2022. Likely is going to be there, and it's going to be in collaboration with the Conference of Computation and Neuroscience, and together with the guys who recorded the so-called natural scenes data set, which is, I think, the best and largest 70 extremely high quality data set that ever was there of visual responses. And they were so nice that out of the up to 40 sessions that they recorded for every participant, they actually keep 2 sessions hidden. And we can use those 2 hidden sessions secretly to evaluate models that people build on the free release data to see how well their models actually do on a left out data set. The second thing that will help, that people say is often more data, in the sense that these deep networks are trained on millions of images. Evaluating brains is costly and difficult, so we often end up with maybe a couple of dozens or hundreds of conditions. So if you look at this in a classical design and in psychology, you have maybe 2 to 4. RSA, typically, it's not limited to this, but people often use something like 20 to 200. Compared to millions, this is still little. There is large to big scale efforts to record a lot of different conditions like BOLD 5000, which has 5K, or the NSD data set, which has about 30 to 80K of different conditions. So, and the idea there is, okay, if you really want to say something about the richness of the representations that the brain must have to represent the richness of the world, and you must be able to differentiate between models very well that might be right now very similar in terms of how they perform. You just need much more data and much more or a much stronger testing ground. So we said, yeah, that's true. And people provide this for fMRI. So we're going to do something in the spirit for EG. So this is some work by Alessandro Gifford, which has done the following. So based on the THINKS initiative by Martin Hebert, many of you might know this, he took the images from 1,654 different objects, and he took 10 different images of those, put them into a training set, and another set of 200 images into a testing set, which together gives you something like 16,540 different conditions. Now, 16,000 is still not 1 million, but it's definitely a lot more than maybe 100 or 200. Now, if you want to show 16,000 different conditions to a human being, it's going to take a long time. So you just take a little trick that has been around in monkey research for a very long time. You just use rapid serial visual presentation. So for example, we just do trains where we show an image for 100 milliseconds, blank screen for 100 milliseconds, and we continue doing this in very long streams so that in a very short time, we actually get a lot of trials in. So in this way, Ale actually recorded in 10 subjects EG data for 16,754 conditions in 4 repetitions, which is something around 80,000 trials per person. Then, using the type of approach I've just shown you, the encoding models, he asked, okay, can I build a proper encoding model on this, something that will actually predict brain activity well? And the answer is yes. So he took different deep nets to do this, evaluated them. On the x-axis you see time. On the y-axis you see how well you can decode based on the output of such models. And you can see on this curve, this is pairwise decoding, so chance is 50%. And already when information reaches cortex 60 milliseconds, it goes high up to 90%, and then goes down. So actually, yes, you can have a rich sampling of stimulus space with so many conditions. And this luckily does not only work for the average of subjects, but it works in every single participant. So maybe going back to one of the questions we had, how similar do people have to be? Now, this is maybe a question that we can now start addressing at a much fine-grained level. So we can ask how similar is participant 1 to participant 2 in a particular way. What are the systematic differences between them? So now I've shown, okay, we can use this to build particular models, but we would like to know also how rich is this sampling actually. And the good thing is that once we've built our encoding model, the model which takes us from a particular model through the brain space, we can not only do this for the images for which we actually recorded brain data, we can do this for as many images as we wish, for which we did not have recorded brain data. And then we can ask, okay, if we do this, can you still find the right image and the right brain activity? Can you match them together? Or is the algorithm becoming confused? Because if I give you 200 images, maybe it's simple to say which one of the 200 it was that fits this brain activity. But I give you 100,000 images, it might be a lot more difficult to say, oh, it's still this one out of 100,000, and more difficult than to say, oh, it's this one out of 200. So we did this. And what we find is that if we just look at the activity or at the brain activity that we have recorded, the 200 images, the identification accuracy, how well you can say, oh, it's that particular image, is about 80%, where chance level is 0.5%, 100 divided by 200. But if we add up to 150,000 images, we still are way above chance, which means that this is a very rich model that even if you very strongly increase the competition and the difficulty of the task, still performs well. Now, this takes time, so we can't keep on doing this for more and more and more images. But what we do is we just fit a line here and ask, when does it hit a particular value, for example, 10%. And if we do this, we still find that we would be above 10% if we were to put in 3.65 images. And if you wanted to go down to the chance level at the beginning of 0.5%, we would go up to even 16.2 trillion images, which is a crazy number. All it is meant to say is just to say that it's possible to distinguish a really large amount of visual cognitions, and that this data and this type of modeling is really rich. Okay. I would now like to close with something completely different, which is, I told you, many of the things that we're using can be used to deal to look into other cognitive functions as well. And Alex introduced me as someone who cares about philosophy. So at some point I started thinking that right now we always look at concrete objects or concrete concepts like faces, potatoes, bananas. And if you come from philosophy, you start caring at some point, okay, what about these abstract things like development, politics, beginning, end, help, love, religion? Can't we use all the techniques that we have to study the representation of concrete objects to study the representation of abstract objects? So we did one fun experiment. This was done by Daniel Kaiser. He now has his own group in Gießen, where we did the following. So we invited people to come to the scanner and we gave them some crazy story. For example, imagine you're an astronaut exploring faraway galaxies. There you meet members of a previously unknown alien race. Try to explain humanity and its culture to them. And we would show you a set of these abstract concepts in random sequence, and they would have to keep on telling a story on this in the background. And we would do this in 10 different ways for 10 different stories. And then we would go to our standard motions. We would extract neurorepresentational similarity matrices in the searchlight in the brain and just ask, okay, which of those words or concepts is the brain treating at a particular place in the brain as similar or difficult or different? And we would then compare it to different types of models that are believed to capture some aspects of semantic meaning. So the most simple you can take, it's the sister of AlexNet in terms of linguistic models, it's word2vec, which just captures the co-occurrence statistics of words in corpora in a particular way. And we ask, are these two things somehow related? And if we do this, we actually find, yes, they are. In particular regions of the brain, like IPC, on the left or the right hemisphere, we find that abstract word meanings are represented in the code of linguistic context, which then is not about where does it activate the brain. We don't care so much about it. We know that the brain activity is there, that the brain regions are activated there when you think about abstract concepts, but in which format might those things be there? And we just provide one idea or one proof that you can use those objects or use those methods to investigate those questions. So because my hour is up, I would like to summarize. We follow two aims here. One is using a technique called MEG or MEG fMRI fusion with resolved visual information flow in space and in time. This is a new approach to investigate the dynamics of neural representations for, I would suggest, whatever cognitive function you care about. And it also allows you the identification of when representations relevant to a cognitive functions emerge, for example, if you start pairing it with behavior. And the second aim, we have compared deep networks to the human brain. We've shown you that there's a spatio-temporal correspondence between models in the brain, and I've shown you some research efforts, how we try to bring this to the community, for example, in the Algonauts project, in an open challenge to compare more brain models towards each other in a faster pace, and how we try to also provide the data that will invite or inform model comparison on a high quality basis. So this together is then a novel way to elucidate the algorithms behind object recognition. Now, I would like to close with the acknowledgement and thanks to the lab, the people that really did the work, all collaborators, the collaborators at MIT, which were fundamental in starting this research and taking off the ground, and of course, all funding bodies. And happy to take any question you might have.
Can I ask a question?
Yeah, of course. Go ahead.
I'm just out of curiosity because this is something that you did not touch. By the way, my name is Vahid. My apologies that I don't have a video available at the moment, but as something you did not touch in your talk, and this is something I asked because it's of interest to me from my own research, and that's the relationship between this visual perception and also the gaze behavior. So is it something that you have ever dealt with? And in particular, I'm interested in this neural network model that you have made the correspondence between that and the neural activity. Also, have you extended this work into studying gaze behavior in humans or maybe in non-human primates? Thank you very much.
Yes, thank you. No, we have not done this work, but I think there's a great basis for this. So for example, out of Tübingen coming is a network called Deep Gaze, which is, I don't know, the different networks always battle each other on a weekly basis. I don't know whether they're still the best, but they are a very good network, I think still, of predicting for any arbitrary image, where in this image you will actually gaze, where you will fixate. I think there must be representations in those networks which should be able to be matched onto either parietal or, I don't know, frontal eye field type of representations that should also predict you how, in a bottom-up way, you calculate the salient. So whatever it is that this model is calculating, and you actually could find out what it's calculating and where in the brain this is related to. By doing this model comparison with brain activity. Now, we don't do this because we most often just have a very classical background. We ask people to fixate and not make eye movements. One of the problems of eye movements, of course, is that you do get strong artifacts of particular ways in EEG. But again, there is ways of dealing with this. So I don't think it's impossible. It just takes someone who says, I'm going to put in the effort and do it. And again, there's people in Tübingen, I think Benedikt Ehinger, who is just working on this type of EEG analysis that would correct for particular eye movement artifacts.
Hi, can I ask my next question since no one seems to be, no one else seems in competition? Okay, so the part where you talked about how, how your box cells light up, right, for different visual stimuli. I'm curious about this part on two levels. The first one being like how granular can the stimuli be? Like, I know you're showing bus and apple, and that's quite far apart, right? But like, how close can they be together for it to differentiate and light up differently? And then the second question is, because I study V4 myself, I'm kind of familiar about how different parts of the brain react to like, different pieces of the stimuli. So for example, if you were showing a bus, it wouldn't be processing the bus as a whole at some point, it'd be processing pieces of it. So when you see this lighting up in the fMRI, how can you tell which parts are actually, the proponents for triggering that response, and which are just like, artifacts?
Yeah, good questions. So the first is how big can the differences or small between stimuli be? That's a function of the SNR sampling of your methods and the spatial scale at which, that's for fMRI, let's say, and the spatial scale at which your stimuli are represented. And this is something we don't really know. We believe that something at the columnar level might be very important, right? So 1 millimeter by 1 millimeter, if you had that resolution, that would be just fine if you believe that a columnar organization is basic. One way we tried to get at this with with MEG, was by asking, can we distinguish between gratings of different orientation in MEG? Because supposedly in V1, at least, different orientations are represented in different columns, which are then, arranged in pinwheels. And if you show different orientations and you can distinguish between different orientations, that means that you can distinguish between activity at the level of cortical columns. Now we tried this. Of course, this is an uphill battle because there's always a potential confound you could have. And then we actually, that was work 2015. We scanned, I think, something like 80 subjects. We did 5 experiments testing for all different types of confounds we could think of and people hadn't brought up, because we had a very similar debate like this in fMRI, asking at which level does decoding actually work? Can we distinguish fine-grained information, or is this all like broad-scale information? And we found that, yes, we can decode between different orientations. So potentially, it's not impossible that we can look at very fine-grained information. It's very hard to really give you a good answer because we don't ever know the ground truth. I mean, probably for ground truth, you would have to have something like voltage dye imaging in a very particular region and only activity in that region. And if you were then to combine this with fMRI and MEG, and like in an in vitro part of brain, then it might work. But because there's always the rest of the brain in it, and there's things we didn't think about and artifacts from all ways, I think you can build plausibility arguments, but you can never have, right now, we don't know. We must know much more about the topography and the spatial frequencies at which particular types of information live in cortex, and we just don't know this. But definitely it doesn't have to be radically different things. And if you look at this, I mean, we have here 16,000 stimuli. These 16,000 stimuli are pretty different. They come from 1,650 different concepts, but again, there starts to be a lot of overlap. And if you can distinguish between millions or trillions of images, that gives me some confidence that yes, actually we're tapping into very rich representations, which are pretty small. Another rule of thumb to use is that if there is a perceptual difference, there's likely also going to be a coding difference, or it's going to be differently. Just very pragmatically, not making statements about consciousness. If you have a perceptual difference that's big, you're going to have an easy time finding it. If you have differences between stimuli that you can barely see, that's going to be really tough. So that's it. Now, the second thing is you asked me, okay, we do this analysis at the level of images and you care about V4, which likely has smaller receptive fields than maybe IT, and it looks at object parts, and people have shown that it responds most strongly to particular curvature parts, maybe, and it's surely not the whole thing. I agree. If you do the analysis at the level of images, you can't go beyond that. But you could, for example, say, I don't know whether you work in monkey or humans. But one way, or other model species, one way to go about this would be to include retinal information. So if you know the receptive field of your neuron or your voxel, you could start limiting the analysis to that receptive field. Why look at, if you look at V1 and you want to predict activity in V1 in this part of the visual field, why are you looking at this stuff over here, right? Doesn't make sense. So that would be something like a first step towards narrowing this down. And then you have a nice space. And then you can try to find the, let's say, principal components, or you can try to use any type of data. It's basically, data analysis, large scale data, and trying to get the underlying latent factors, whatever you have, to find what might be driving this in pixel space. If you want to go beyond pixel space, you might want to have a parameterization of your stimuli. So again, I don't know what you're working with. If you work with natural stimuli, things are difficult. But you could have, for example, 20,000 different artificial stimuli for which you have 100% control. Basically, I don't know, in whatever space you build them, SNRPs, anything you wish, you know exactly what the surface normals are, the distances, the colors, blah, blah, blah. And this is a much lower dimensional space. You can look for similarities there. So I think in vision science, you had these two camps, right? One is artificial stimuli for maximal control, natural stimuli for ecological validity. It's going to take both. So that's a long answer to this.
Okay, in light of the time, I would suggest we finish the meeting now. Thanks again for the fantastic talk. Great overview.